for you on Canvas, right? So you're welcome to take a look at that anytime that you'd like. And of course, most specifically for this this lecture, and we'll continue this discussion on Friday, and then of course into Monday. By the time we get to Friday's lecture, you're going to have everything that you need to be able to write project number 4. Okay, so after Friday's lecture, you'll be able to write project number 4, and then after Tuesday's lecture, you'll be able to write exam number 2, right? So exam number 2 is a take-home exam that will be posted on Canvas next Friday. I think it's Friday, May 5th. And I'll post a sample exam, hopefully by Friday if I'm able to. And that sample exam will very nicely prepare you for exam number 2. There'll be a review session that goes through the solutions of that sample exam and get you fully prepared for exam number 2, okay? All right, so basically, what are we doing here now, right? We've reached this final chapter, chapter number 7 of the class, spark ignition combustion. What exactly are we doing, right? What is this discussion? Well, what we're doing now is we're basically recognizing that combustion is something that takes a finite amount of time, right? To this point, so far this semester, especially when we got into chapter 3, 4, and 5, we basically assumed that combustion could be something that either happens instantly at constant volume or happens in such a regulated fashion that it maintains constant pressure in the cylinder, or is some hybrid of the two where some of the combustion happens instantly at constant volume, but then the rest of the combustion happens at this controlled fashion of constant pressure, okay? Well, those 3 situations are highly idealized, right? They don't ever happen in practice. We never achieve constant volume combustion. We really wouldn't want to achieve constant pressure combustion, as I'll explain in this chapter, right? And so they're basically just convenient ways to do the thermodynamics, right? To be quite frank with you, right? It's easy to do constant volume analysis. It's easy to do constant pressure analysis. We learned from exam 1 that it's not as easy to do constant temperature analysis, but we can do that too, right? So this is all basically just to make the mathematics, the analysis of the thermodynamics easy. In reality, combustion takes a finite amount of time, and we realize that that finite amount of time can be controlled by us, and it has lots of implications. It has implications on how much power we make. It has implications on the efficiency of the engine, and it has implication on the emissions of the engine, right? Again, these 3 things that we're always thinking about when we design and develop internal combustion engines, okay? So what does this finite time, this finite combustion process look like, right? And of course, you've already seen videos about this. We showed videos way back, like in the first week of class, where you had a chance to see what combustion looks like, with a video camera, for example. But basically, we can sort of discretize spark ignition combustion into 4 major events, right? 4 major things that happen over the course of this spark ignition combustion event, okay? The first thing, basically the thing that kicks it all off, is the spark release, okay? So we have a spark plug that's mounted through the cylinder head, and the electrodes of that spark plug, basically, there's what we call a gap, where you have your anode, your grounding strap, basically, and then you have your cathode, and we have an ignition system, an electrical ignition system that delivers an extremely high voltage potential to that cathode, right? Extremely high voltage, we're talking thousands of volts, right? And that's all, of course, done by the ignition system. There's a step-up transformer, a distributor. That step-up transformer, we call that the coil, right? There's some kind of a distribution system that regulates which plug is going to see that voltage rise at any given time. Old-fashioned ignition systems used to use mechanical distributors, where you had this rotor that would rotate at the same speed of the engine, and that rotor would basically rotate within your distributor cap and basically deliver the voltage to whichever plug was to receive that high voltage at that time, right? And that was how you made sure that the timing of the engine was correct. You set the firing order of the engine based on how you connected those plugs to your distributor cap, right? Well, that technology is long gone, right? Maybe regrettably, I don't know. But you now have basically electronic ignition systems where you have your coil is basically integrated into the plug itself, the plug wire, excuse me. And so you have your plug wire that has all of this integrated electronics, this ignition system integrated into it. And you have an ECM, an electronic control module, that's basically sending a signal to every plug wire saying fire now, fire now, fire now, right? And so that's basically the modern manifestation of a distributed ignition system, okay? Anyway, that voltage is sent to the cathode of the plug. And of course, there's a potential difference between the tip of the cathode and the grounding strap, right? And so there's a current that then flows between that cathode and the anode. And for a very, very, very short period of time, like nanoseconds period of time, a little plasma is formed, right? You're saying, that current flows and it ionizes the gas and creates a plasma for a short period of time. But the voltage potential is so high that plasma essentially immediately breaks down and an arc is formed between the cathode and the anode. And that's what's referred to as the spark, right? The moment that you can see that electrical arc, that what we call discharge, right? That electrical discharge, that arc is basically the spark, right? And so you're dumping voltage, electrical energy into the mixture. It's actually not a lot of energy, right? It's usually on the order of millijoules, right? So it's a small amount of energy that the spark is delivering to the mixture, but it's enough to cause the temperature of the fuel air mixture near that plug to rise, and to rise high enough that the fuel air mixture can start to undergo combustion chemistry, right? In other words, your hydrogen and your carbon begin to separate from the fuel, and they begin to form intermediate and radical chemical species. There's literally like dozens of species that are formed during the combustion reaction, and literally hundreds of reactions that take place. It's more than just CH4 interacting with oxygen going to CO2 and H2O. There's all kinds of intermediate steps that take place, and it all takes place during this spark ignition combustion event, right? And most specifically during the sparking event, okay? So basically, this figure A that you see here, this is basically, right after the spark has been released, okay? And so these 6 little images that you see here are basically what we call Schlieren videos, or they're picking up the difference in density in the mixture as the mixture changes as it's undergoing this SI combustion, right? So this little bit of distortion that you see here. So this is your spark plug right here, and this little bit of distortion that you see in the mixture is basically a density gradient that's created by the release of that spark, right? The density gradient caused by the change in temperature affected by the release of the spark, okay? And so you have this this perturbation, this spark that's released, right? And then of course what you see is that density gradient, it basically grows as you go from image A to image B. It grows, and then it starts to essentially blossom into what we call a flame kernel, okay? So a flame kernel is essentially where we now have what we define as a flame, okay? So a flame is as you might expect, a region where the chemistry is taking place, the combustion chemistry is taking place, where you have fuel and air feeding the flame from one direction, and you have products of combustion coming out of the flame on the other side of the flame, right? So the flame itself is a rather thin region where the actual combustion chemistry is taking place, right? The fuel and the air are reacting with each other. That's where all these intermediates are formed. That's where all these radicals are formed. And all these reactions are taking place, where eventually you have fuel and air going into the flame, and then you have CO2 and water and other products of combustion coming out of the flame, okay? And so that's your flame kernel here, right? That's where basically flame front is starting, okay? As that flame kernel develops, we then transition into what is called turbulent entrainment and burnup, okay? So turbulent entrainment and burnup is basically the result of this flame kernel having developed. And of course, as that flame is developing, the temperature and the pressure of the mixture is rising, right? So you are releasing energy from this combustion reaction as this flame kernel develops, right? And so the temperature and the pressure of the reaction are rising. That causes the mixture to become very agitated. It causes the temperature of the whole mixture, the unburned fuel and air, to become more turbulent, as we say. And as that turbulence develops, the flame now has an opportunity to basically spread very rapidly throughout the mixture. There's a little diagram that I'll show you on Friday that kind of illustrates for you what this turbulent entrainment might look like, right? But you can almost think of it as like fork lightning, right? If you've ever seen fork lightning in the night sky, you sort of have this lightning that's just branching off in all these different directions, right? Or even just think of a tree, right? If you think about all the different branches of a tree, and the tree is growing its branches out in all these different directions, right? Or that fork lightning idea where all these different arms of the lightning are touching all these different regions of the sky. Well, that's what turbulent entrainment is like, right? It's almost like it's carrying the flame to all different regions of the fuel air mixture, and it's causing that fuel air mixture to start burning in multiple locations of the mixture, right? It's spreading flame to multiple regions of the mixture. And then once you spread the flame to these different regions, now you get these little pockets of fuel and air that basically burn up, okay? And so that's what you're seeing here in images D and E, is that turbulent entrainment, that rapid spreading of the flame through the whole fuel air mixture, and then the subsequent burnup, okay? And then, of course, eventually you're going to run out of fuel and air, right? And you're going to terminate your flame, okay? And so this image F is sort of the last sequence of the combustion process, the spark ignition combustion process, and it's where you basically have your final burnup, your termination, okay? So in terms of timing of things, and again, we'll cover this more here in the next slide or two, but basically in terms of timing of things, the processes that go from A to B to C, this takes quite a bit of time, right? On a relative basis, right? This might take, in terms of the whole combustion process, this might take the majority of the time to get yourself from the release of the spark to where you now have this flame kernel, right? And then turbulent entrainment, the flame captured by images D and E, that happens very rapidly, right? That might only require a quarter of the time for the total combustion process. And then finally, image F takes up the balance, right? Which might be more than a quarter, whatever that balance is, perhaps not as much time as the flame initiation period takes, but definitely much less time than the rapid entrainment and burnup period takes, okay? Okay, so now that we kind of understand the stages of SI combustion, we can now link this back to what's going on inside the cylinder in terms of cylinder pressure, right? And this is something that you'll start to see when you look at your cylinder pressure versus crank angle data for your project number 4, right? The real engine data that you're looking at, okay? And so, of course, you can start to see the whole process, right? You can see when, well, first of all, let me back up just a minute, right? So what we're looking at here is cylinder pressure versus crank angle, right? And so this line here, you can tell by this arrow here, which is pointing to the cylinder pressure axis. This curve that you see here is the cylinder pressure versus crank angle curve, okay? The second curve that you see here, this is what we call the mass fraction burn curve, okay? We're gonna talk about that more in just a little bit. But you can see what mass fraction burned is basically quantifying for you is what fraction of the fuel have I burned as I'm going through the combustion process, right? So obviously, before combustion even begins, I've not burned any fuel, right? But then combustion begins and I start burning fuel, and then that fuel burning rate increases, right? So this would be the rapid, I'll take you through all of this, but this would be the rapid entrainment period. But then eventually I get close to burning all my fuel, and that burning rate begins to slow down, and I enter into the flame termination period, right? And so this is my final stage of the combustion process. And of course, if I've done a good job designing my combustion system, then when I get to the end of the combustion process, I will have burned all of my fuel, right? So the mass fraction burned is 1, meaning 100% of the fuel has burned at that point, okay? And so, of course, everything starts with a spark, right? So I release my spark, and this timing at which I release the spark is what I call the spark timing, okay? We're gonna talk more about that when we get into Friday's lecture, but you can basically see here, right, that, you know, this is top dead center, 0 degrees crank angle. This is 20 degrees before top dead center, 40 degrees before top dead center, 60 degrees before top dead center. So, you know, roughly halfway between the two is 50 degrees. And so my spark is a little bit closer to 40 than that midway point. So the spark timing is probably somewhere around 40 degrees, right? 45 degrees. 45 degrees before top dead center is when this spark is being released, right? So think about that for just a minute. We have to release the spark a full 45 degrees before top dead center in order for us to have a combustion process that mostly takes place after top dead center, okay? Let me repeat that. We have to release the spark 45 degrees before top dead center so that we can have a combustion process that burns the fuel mostly after top dead center, right? That's how much time it takes to initiate the flame and develop that flame kernel for us to then trigger into the rapid entrainment and burnup period, okay? Okay, so we can then see basically what the pressure curve looks like as we initiate this flame and develop that flame kernel. So the A here indicates that this is the timing that corresponds to frame A. This is the time at which the pressure curve corresponds to the flame at image B, right? The same thing for image C, okay? And you can basically see that, you know, more or less this looks like a typical what we call motoring curve, right? So what does that mean? What is a motoring curve, okay? Well, this curve that we're looking at here, this is obviously the pressure curve that results from when there is a combustion process. But what would the pressure curve look like? What would in-cylinder pressure look like if we didn't have combustion, okay? That's what we call a motoring curve. And essentially what that looks like is it's gonna be very similar at first to our firing curve, but then as we get to top dead center, it's going to basically reach its peak and then begin to decrease in a symmetrical fashion to our compression curve, okay? And so this would basically be what we call our motoring curve. That was really hard for me to draw, so let me draw this here so that I can try to make this look a little bit better. So this is our pressure, and this is our crank angle. And say this is top dead center here. And so if this is our pressure versus crank angle for the motoring case, it's a little bit hard to draw on this because the iPad is at an angle. Then our firing curve would look like this. Okay, so this is firing, and this is motoring. Okay, so you know, clearly this is a firing curve, right? Because we have that firing curve characteristic, right, where we have the rise in pressure after we get to top dead center. And so right at top dead center is basically when we trigger into our rapid entrainment and burnup period, right? And that's of course when now we have the most fervent combustion taking place, right? And we then approach the end of combustion. And so now the rate of combustion begins to slow down, and the mechanical motion of the piston expanding the cylinder, right? Remember that we're at top dead center here. And so we are now expanding the piston during the expansion stroke. Combustion has ended. And so that cylinder pressure begins to decrease as the piston is expanding the cylinder. And then finally, we get to the end of combustion, our flame termination period here at point F, okay? Okay, so those are the different stages of our combustion process and what they look like on the pressure versus crank angle diagram. And what we'll pick up with on Friday is we'll start talking about this mass fraction burn curve, and we'll relate two important definitions on the mass fraction burn curve, specifically what we call the flame initiation period, this delta theta D, and the rapid burning period, this delta theta B. We will relate that, we'll characterize the mass fraction burn curve with these two parameters, and then relate that to our in-cylinder pressure, and then ultimately relate it to our torque versus spark timing curve, which of course is going to help you substantially with project number 4. Okay. All right. Well, that's all that I have for you today. Thank you so much for your time and attention. And I look forward to seeing you in class on Friday, and I wish you a great rest of the day. Take care. Bye-bye.